you're multiplying it by beta, so you're pushing it that way. If an example falls here, you're going to push it that way. So you're forcing the tree to make hard decisions to favor hard decisions instead of soft decisions. And the other trick is that, well, since you're introducing these hard decisions, it is very likely that the tree will always favor one branch over the other. So you have branches that are not trained. So the other, I'm not going to write the formula because it has a lot of sub-indices, but I'm going to show it to you. Well, here you have the loss function that is used to train the tree. It's a form of negative cross entropy. So if P is P is the path probability of that branch. So you multiply that probability by that probability by that probability, you get the path probability of this branch, and so on for everything. Observe that for every example that is perfectly defined. Okay, it's not after the tree is trained, you know all the path probabilities. So if your example ends up here, you know that path probability. That is the probability of the leaf. Then you got the actual distribution. So that actual distribution is where distillation comes in, because that so that one can be either the hard targets or the soft targets, or a mixture of both. Yeah. So in the examples that they show later, they use that loss function. So if you replace cross entropy by that, and you replace the targets by either the hard targets or the soft targets, then you get this loss function. And Q is this probability over all the classes. Okay? So the loss function is trying to find out which is the best branch for each example. The problem is, like I said, that is going to tend to overfit, so it's going to try to put each example in a single branch. And ideally we don't want that, because maybe an example can be explainable this way, on this branch or on that branch. So they put a heavy regularizer, which is basically trying to make the tree trying to make each leaf use both branches equally, each node to use both branches equally. Okay, so at each point you have the probability of each branch, which again is defined, times the probability of each side, which is the sigma, and then you apply a regularizer over all the nodes that is trying to force the tree to use both branches symmetrically. And that is basically it. So with that training algorithm, you have a tree that can be distilled from a large neural network.